Go.
Good morning, ladies and gentlemen. Let's talk a little bit more about waves. Waves at a boundary. Waves at a boundary. When a wave encounters a boundary between two media, some of it is reflected and some is transmitted.
What the heck does that mean? Can you demonstrate
Okay.
that?
All right, so we're gonna go ahead and demonstrate a wave using our slinky here. And we have two different media. We have the slinky and we have the string. And what's gonna happen
That right
is,
there is a boundary between the slinky and the string.
yeah, well, let's go ahead and just try this out, and we'll talk about what happens. So I want to make sure I stop at equilibrium right here, right?
Okay, so you're going to send a pulse, and anytime you're ready. Oh. Oh, I noticed that pulse came back on the same side.
So think about our lab from a couple days ago, and we're gonna call this, a loose end. It's not fixed, right?
Yeah.
It's able to move around. And so what happens is when the pulse gets set through, the slinky, the medium, the slinky,
Yeah.
some of it is reflected back.
Goes
and when
back
it's
down the
reflected
slinky.
back, it goes on the same side that I set the pulse on, right?
Yeah.
And then also some of it, you can see the string wobbling here,
Yeah.
gets transmitted this way.
So
through the
that's what we're
string.
talking about. The boundary between the slinky and the string is right there. And some of it is reflected and some of it is transmitted. That's an important idea.
All right, so let's talk about like the media and how the media makes
Yeah.
a difference. When a wave goes from a less dense to a more dense medium, the reflected wave is inverted on the opposite side.
And we saw that in that lab we did yesterday, and you can also demonstrate it with that hanging spring
Oh
right
yeah,
there.
yeah. Okay, so all right, so we have when a wave goes from a less dense to a more dense. So,
So
it's going from the slinky to
Where that attachment on the wall, where the attachment on the wall can't move, it's more, you can think of it as being more dense.
it's solid, and I'm going to go ahead and send the pulse this way. Well, how will it be reflected back?
Comes back on the opposite side.
Right? I'm a little tighter here. Right? So we said it, right? That we see.
You
how
can
it's
see it comes
inverted.
back on the opposite
Yeah,
side.
this is easier to see than that one.
Yeah.
Okay.
So that's called inverted. When it comes back on the opposite side, it's called inverted.
And that makes sense because a more dense medium is just like it being fixed.
Right.
I mean, right? So,
Yep.
and then we just saw this from a more dense to a less dense. That's just like our.
The slinky is more dense than the string, and so it comes back without inversion.
No inversion and the same side. And we saw that in our lab too.
Yeah.
If you're like, wait, I didn't see that, go watch the video again in slow motion. Okay, so a standing wave. Should I go ahead and demonstrate?
Yeah,
first?
just show them.
Okay. What the heck is a standing wave? We've got some words up there that we don't know about yet.
What happens if you stretch it, hold it right about here.
Right there? Okay.
Yeah.
All right, so
If you send one pulse,
right now we've just been talking about
1,
sending
2, 3,
a
4,
moving
5,
wave?
6, 7, 8, 9, 10, 11, 12. Oh, that goes back and forth, man.
Yeah. And then what happens if I send two pulses? It gets all wonky, right?
Well, what happens is they're going in both directions.
Yeah, well, and so, why do we get that chaos? I sent my first wave, and then shortly after I sent my second wave, right?
Yeah.
And this one, inverts, and then this one kind of
Oh, and you get destructive interference.
They move through each other, and then it happens all, and it's freaking out, right?
Yeah.
But those are not standing waves.
Those are traveling waves. They travel from one
Yeah.
place to another, from where you had it
From
down to
your
the other end.
Okay, so a standing wave occurs when incident waves, what's an incident wave?
Incoming.
An incoming wave, interfere with reflected waves that are coming back, at exactly the right frequency. And who controls the frequency?
You do.
Me. Okay. So let's see if I can do this. Should I start with one? Just one?
Well, no, just.
I can do? Okay, here we go. This more is a work in progress.
Okay, so
here.
you're not. See how little she's moving her hand,
Yeah.
but. Okay, now you're cheating.
I know. It's hard.
It's all about the frequency. It's all about the rhythm. And so what's happening here is you're sending pulses down there and they go back and forth many times. And so pulses going that she's sending, continuing to send with this, interfere with pulses that are coming back. And that's called a standing wave. Notice it looks like it's not going anywhere. It's just standing in one place.
Yeah.
All right.
Should I see if I can get more? Or should
Well,
we just...
yeah, see what you can do. Yeah.
So, okay. So it's harder than it looks, ladies and gentlemen. What can make it look easy? Really try not to use my only.
Okay, now you're moving your hand faster.
There we go.
And see, she's not moving it very much, but she's getting big bumps.
Yeah.
And there's places where you get big bumps. And you get places
Show
where,
the bumps. Show
where
the
nothing,
bumps.
where nothing is happening.
Okay. And we can talk about here if I can multitask. You know, so we've got this spot in the middle that's kind of staying there. What's happening here?
Now the middle is going to be right here.
I'm sorry. I can't multitask. So we see those bumps and we have those spots where it looks like it's just standing still right there.
Now let's go to the next
We're
slide.
going to talk about what's going on. All right, so destructive interference produces nodes. Okay, so our nodes are right here in this spots right here.
That's where you've got a pulse on the top going one way meets a pulse coming back on the other side. A crest going one direction with a trough on the other direction.
Yeah, I mean, we talked about, 1 + 1 and a -1 gives you 0.
That's right.
Right? And so it's a crest and a trough, and they're canceling out there. And we call them nodes. We're giving them a name. They're called a node.
See if you can make a standing wave again and show that.
Can you find the nodes?
Yeah, don't, give it, stretch it out a little bit more.
More
No, no,
space
no.
there? Oh.
Stretch it.
Oh,
Stand
stretch it
right
like
about-
that.
There you go. You got to hit the right frequency.
I know. He's got to find the right frequency. There
It's
we
all
go.
in the wrist, girl. All right, so right here, we've got a node. Now just stop sending pulses. Okay, and that node is at equilibrium. That's because you had a crest going one way, meeting a trough coming the other way. They cancel each other out. All
So
right,
this is equilibrium right here, and you're saying the node is just wherever the equilibrium
where
is?
equilibrium is, that's right. As if you weren't sending pulses. And that's because of destructive interference.
Yeah. Okay. How about what happens when we have constructive interference? Well, this produces what we call antinodes, and those are the bumps. That's where our amplitude is being increased. That's when we have a crest and a crest meeting, or a trough and a trough.
And they get your constructive interference. Yeah. So that's an antinode.
Antinode. Okay. Let's see what I have here for this one.
Well, we got a demonstration here.
Oh yeah, right here. Okay, so so this is one wavelength, and one wavelength is 2 bumps.
Two antinodes, 2 bumps.
Right here, right? And then we have one right here,
Yep.
right? And so we have our nodes are where it's at equilibrium, which would be right here.
There's no movement.
Node, and then here's an antinode, here's an antinode, here and here. And this is one wavelength here.
This is an important idea. Standing wave doesn't have to be a full wave. And because you did half,
Yeah.
well, let's see if we can make some waves. See if you can start off with half a wave.
Ooh, good idea. Okay. All right. So what would half a wave look like? Just one bump.
One
right?
bump would be half a wave.
Okay, so let's see if I can do
You
this.
stretch that out some more. There
Yeah,
you go.
I
There you
can.
go. There you go. All right, real slow. Okay, so she's hardly even moving her hand at all, and there's half a wavelength.
So what would a whole wavelength look like?
Well, you'd have to move your hand faster.
Okay. Oh no! What would a whole wavelength when I move at this pace look like? It would be double the.
Oh, it'd be twice as long.
Twice as
So
long,
that's
right?
half a wave. The whole wave would be out.
there.
Yeah,
Okay. What next?
that's a great question. Move your hand a little bit faster. See if you can make a full wavelength. Not too fast. See, there's 3 bumps. So that's 2 bumps is one wave.
There we go.
Now there's a full wavelength. You've got antinode, node, antinode, just like in the drawing.
And 2 bumps. Look at that.
2 bumps is one wavelength.
Okay.
Good job. And then you
So-
can move your hand faster. It's all in the wrist, girl.
I know. There we go. I'm getting better at this.
There's 1.5. And all she's doing is changing the frequency. The speed of the wave stays the same. She changes the frequency, and that changes the standing wave that's produced.
Okay.
We don't have to do the rest of these. Those get really hard.
Yeah.
Wears you out, doesn't it?
Yeah, my forearm. Okay, so again, this is a really important concept. You just saw a standing wave. You saw a standing wave that was half a wavelength and a full wavelength, and then 1.5 wavelengths.
Yeah, but you can have 2 wavelengths. And how many wavelengths is this bottom one?
Okay, well, every bump is a wavelength, right?
Yeah.
So
No, every 2 bumps.
Every 2 bumps. Sorry, 1, 2. This is 3 wavelengths.
3 wavelengths.
Yeah. So a standing wave doesn't have to be a full wave. It can be a fraction of or more than a wavelength. Cool. All musical instruments have a source of vibration and some method of changing the length of a standing wave. So, should I start with these or these?
No, these are musical instruments.
Okay, so we'll start with this one. So, how would I change the length of the wave here?
Well, the source of vibration is that blue mouthpiece,
Okay.
and then you can change the length of the pipe. Don't quit your day job. But but you could see as she opened it up, she shortened the length of the pipe.
Yeah, and then what happened to the pitch there?
It went up.
Okay.
The frequency increased, and you were changing the length of a standing wave.
Okay. Should I try with this one?
Yeah, that's a piece of junk, but it's it's a slide whistle. Yeah.
So again, it's changing the length of the standing wave.
And that changes the frequency, it changes the pitch.
How much of a wave is transmitted depends on how different the 2 media are. And I guess we can just talk about the slinky, right?
Well, yeah, we don't need to go into this.
No?
It's a point, because if there's no difference, you get no reflection. For example, there's a change in the properties of the medium where the string is attached. No string, string. So when you send a single pulse down this thing, there's a little bit of reflection at each one of those strings because there's a small difference. But it's just a small difference, so most of the pulse is transmitted and only a little bit of it. So you can see all the other vibrations that are happening. The whole thing is wiggling. That's because there's a little bit of reflection off of each one of those strings. It's not much different, so there's not a large reflection. But here, where there's a big difference, there's a big reflection. Sorry about that again.
No, and this kind of goes along with those first few slides about, dense or less dense.
Absolutely,
right?
yeah.
Okay. A resonator. What the heck is a resonator? A resonator reflects waves back and forth on at a particular frequency.
You've got a couple of resonators right there.
Resonator 1, resonator 2. Okay, so this is a resonator, and it says it reflects the waves back and forth at a particular frequency. So today we're going to be talking all about a closed pipe resonator.
It doesn't matter. Just slap the end of that sucker. Na-da-da, da-da-da. Now hit the other one.
Okay.
Na-da-da, na-da-da, ya-da-da,
Dying Boykin?
ya-da-da.
Mr. Boykin's in a band. Or at least he was.
So that's those different frequencies, because they're reflecting waves back and forth at a particular frequency. Short pipe, higher frequency.
Oh.
Got a longer, lower frequency.
So the length of the pipe is making the difference.
Yep.
Okay. And when you say it's reflecting back and forth, what do you mean? Do you mean back and forth like this, or back and forth in the thing? Like, what are we talking about?
Back and forth.
Okay,
like
so
this.
so we slap it here, and is this a good time to talk about the clap thing with the bubble?
Yeah, I think so.
Okay, so when I slap the side of this, it's just like clapping, right?
And when you clap, where does the sound go?
I mean, it goes out in a bubble
Right.
around you, right?
Yeah.
And so when you hit this, the bubble is confined to moving this way along the pipe, and it's also confined to...
It can't expand because the walls are in the way.
Yeah, and so once it gets to this side over here, poof, right, it has part of it is transmitted or.
Well, there's a change in the properties of the medium, because right there inside it can't expand. When it gets to the end, all of a sudden it can't expand. That's a difference between the properties. So you get some
of it-
reflection. Yep.
And then what happens to the other part of it?
Reflects and transmits.
And that's the resonator part.
Yep.
Right? Okay. So a closed pipe resonator reflects with inversion from one end and without from another.
Let's see. So it's page 510. What's on page 510?
Remove this stuff there.
I think that's the old book. Nah, it's not this book.
No, we're good?
Yeah, let's see. Well, here. No,
Good.
I don't have that illustration. Sorry, boys and girls.
Maybe next time.
Pay no attention to the man behind the curtain.
Okay. Where were we at? So it reflects with inversion. And what is a closed pipe resonator? Well, we have one side that's, well, this is an example. When I hit it like this on this end, it's a closed pipe because one end is closed.
You keep your hand over it.
And the other end is open.
Yeah,
but
so
one
that's a
end is
closed pipe resonator.
And I think we're going to talk more about that definition here in a second. Okay, there is a quarter of a wavelength between a node and an antinode.
Can you prove that?
Okay, well, here's a node.
Yeah.
Here's an antinode. This whole thing is one wavelength, right? From here to there. And so, well,
The node and an antinode.
2, 3, 4. If we cut that into fourths, this is just 1/4 bit, right?
1/4, that's right.
So that means that there's 1/4 in here.
Yep.
Cool. Oh, so
'Cause
I
you
see.
have-
So
yeah.
you've got one end that's closed, the node, and the one end that's open, the antinode.
Yeah, I like
The
that.
idea? Okay. Okay, so this is important. The loudest sound from a closed pipe resonator is a quarter wavelength. This is the fundamental frequency.
It's called the fundamental frequency. There are other frequencies there that gives quality to the sound, but the main loud sound you hear is 1/4 of a wavelength.
Okay, so let's go ahead and do a little mini lab here. If the speed of sound in air is 343 meters per second, can you predict the frequency of your closed pipe? Should we use this one or that one?
It doesn't matter.
Okay, we'll use this one. So first of all, where am I going with this? If I want to
Well,
find the frequency,
Yeah, go ahead.
okay, so if I want to find the frequency, that's going to be this equation right here, right?
Velocity divided by the wavelength. So the velocity of air is 340. Let's say we considered the wavelength was the length of the pipe.
Okay, so let's go ahead and measure this, right? The wavelength here. Okay, so I'll put it on this side for you guys. Bada boom. Let's just call it 0.35 meters.
0.35 meters.
Okay. 0.35 meters. So that means my frequency should be 343 divided by 0.35. So 980.
980 cycles per second, 980 hertz. Now, you need to go to onlinetonegenerator.com.
Yeah, let's hope I bookmarked it. And the last time I told you I was going to bookmark it. Oh, there's a good chance I didn't though, but that's okay. Okay, if I didn't bookmark it, online tone generator.
Woo!
Good job, Miss Smart. What did I say, 980?
980.
Okay, first of all, play that thing. Oh, can you? Sorry.
Somebody knocked the cell phone out of the.
Let's give that another try. So I'm gonna go ahead and play this.
That is not the same pitch.
That is not the same pitch.
What
Okay.
mistake did we make?
Well, we had just said, I need my thing, that inside of our, if a closed pipe resonator has a quarter of a wavelength in it, how long is the whole wave?
So what mistake did we make?
Okay, so we said that the whole wavelength was just this thing, but it's really 4 times that.
4 times as long.
Right? Okay, so
So
that
you
means
have to multiply.
multiply. Okay, so I'm gonna go ahead and just do 0.3435 times 4. Okay, times 4 right here. So 343 divided by 4 times 0.35. And I get 245.
245. Okay, let's go back over to the sound wave generator.
Sounds more promising. Yeah, because 980, that's like a really...
245.
And I forgot my mouse. Come on, little guy. Okay. 2, 4, 2, 4, 5. Oh my goodness. What the heck? All right.
Nailed it.
There it is.
So what we've just done is we have just proven that there is 1/4 of a wavelength inside that pipe.
Nice. Okay. Woohoo! Feel accomplished. And I forgot my mouse. I need to have just like one of those little like clicky things, you know? Okay, where are we at here? This is our last slide, I believe. The length of the pipe determines the frequency. Okay, so length of the pipe determines the frequency.
Yeah.
So this has a shorter length, so it's going to be a higher frequency.
Yeah.
Longer pipe,
Lower frequency. And that's because it's got a longer wavelength.
Yeah, because the wavelength, there's only a quarter in here, but this one is just like meow. Where this one is like meow.
That's one way of putting
Makes
it.
sense, right? Okay, what if the frequency is fixed and the length of the pipe changes?
I think we can demonstrate that.
Should I do it on here?
And bring it over here.
Oh yeah. Oh, that's right. I forgot it was on. Okay, so the frequency is going to be. I'm going to keep the frequency the same.
The length is the.
Oh, sorry. Go ahead, Boykin.
Just hit it once.
Okay.
No. Keep going. See how the length is? Sweet.
All right. So what's happening there? What's happening to the pitch?
Well, the poster on the inside changed the length of the pipe. It kept getting shorter and shorter and shorter, so the frequency went up and up and up.
Okay.
Kind of like the same as what this thing was doing.
Oh, yes. Okay, so that's all we got here. Your homework today is going to be page 469. Read page 469 through 471 in the AP book. And then you guys are also going to do page 471, number 15.
There's A, B, C, and D, I think. Enjoy.